Okay, so new topic for today, kind of a new topic. We're going to talk about gradients. So we have, of course, talked about gradients previously, right? I mean, it's been an algebraic sort of notation that we've used, kind of shorthand for a special case of a Jacobian matrix. It's a lot like a Jacobian matrix in terms of how it behaves algebraically. Of course, it's a vector instead of a matrix, but okay, fine, so you dot instead of matrix multiply, but it plays that same kind of a role. So, what we're going to talk about today is some geometric interpretations of the gradient. Not just how can it be algebraic notation, but what does it mean geometrically. So, remember, we're looking at real valued functions, right? And we're going to ask a reasonable question here, which is, we've got this real valued function, looking at these real valued outputs. Suppose I am sitting at this point in the domain, and I would like to consider all of the different directions from which I could move, along which I could move from that. Sorry, got a cough. So do some of y'all, but. Of all these different directions that I can move from that point, which one makes the function change the fastest? Right? So we're looking for one of these vectors. I don't know which one it is. Makes the directional derivative as fast as possible. Now you'll notice that I have indicated here of all the unit vectors. Right? We're going to represent directions with unit vectors. Well, yeah. Of course. Otherwise, the question is silly, right? You want to make the function increase faster? Move faster in the domain, right? Well, of course, silly, right? If I'm at some point in the domain, if f is temperature, and I'm cold, and I want the temperature to increase as fast as possible, run as fast as possible. Of course, so that's a given, right? So we're going to remove the silliness aspect by restricting ourselves to unit vectors and therefore actually focusing on the directions. How does the direction that I move affect how the function's changing? Okay. All right, so that's the question. A pretty darn reasonable thing to want to understand, right? Very often we have functions and we want to make them bigger. Profit, efficiency, whatever it is that we're interested, whatever it is that we're studying, sometimes we want more of it, right? Okay, so maximizing, how should I be changing the input to my function to make the thing that I'm trying to maximize improve as fast as possible, right? Very reasonable thing to want to do. Okay, all right, so the resolution is pretty straightforward. This is what we're trying to maximize is the directional derivative. And good news, we have a formula for directional derivative. There it is. Formula for directional derivative, computed in terms of the gradient as a dot product. Oh, hey, don't forget, we know how to compute dot products, right? As a product of magnitudes times the cosine of an angle. So the thing that I want to maximize is this product. And let's take a quick moment to think about what that is in this case. What is the magnitude of the gradient vector? Well, okay, we're presumably at some point A. At that point A, that kind of dictates what the gradient's going to be. The gradient is some vector in the domain that depends on where you are. And so once you've decided where you are, the gradient vector is fixed. The gradient vector doesn't change as you consider different unit vectors. The gradient vector is defined by the point. Okay. So this thing is constant. Okay. What about the magnitude of u? Well, u is a unit vector. The magnitude of that unit vector is 1. Namely, it's always the same. Namely, it's constant. So this 2 is a constant. So, as it turns out, under the circumstances of the question we're asking, if you want to maximize your directional derivative, just try to make cosine theta as big as possible. That's an easy problem. Cosine theta is the biggest cosine theta can ever be is 1. And it achieves that when theta is 0. right? So the answer to this question is, oh yeah, just make theta equal to 0. So specifically then, keeping in mind, we're looking at this dot product between the gradient vector, right? And and this, whatever unit vector we're currently contemplating, u, that theta then is, well, it's the angle between those. If I want that theta to equal to 0, okay, well then what that means is the unit vector, the best unit vector, is the one that points in the direction of the gradient vector. It should be that unit vector. There's your optimal u. Okay. And the way we write that down, of course, is unit vector in the direction of a given vector, vector divided by its own magnitude. Okay. Yeah, everybody on board? Yeah, it's a pretty straightforward calculation. Not that much to it. And okay, all right. So now let's ask another related question. Keep in mind, we're interested in. I want to make this function I'm looking at increase as fast as possible. I've found the best way to make that function increase as fast as possible. Here's the fastest I can make my function increase. And now let's try to figure out, okay, how good of a job are we doing here? How fast is the function increasing? We've already agreed I'm going to move in that direction. So what is the corresponding value of that directional derivative? Well, an easy calculation. The directional derivative that I'm interested in, again, computed by that formula. Okay? And remember, we've already decided that's the best unit vector. So the directional derivative that I'm interested in is just computed by that little formula there. Gradient dot gradient divided by magnitude of the gradient. Excuse me. And of course, gradient dot gradient is magnitude squared. We have magnitude squared divided by magnitude, which is magnitude. Okay. So the way I like to phrase this, the results of this little exploration that we've just done is, there's different ways to say it. One way you could say what we just did is we asked a couple of very reasonable, natural, applicable questions, and we came up with answers. And side note, both of the answers had to do with gradient. Right? The ideal direction is the direction of the gradient. The rate of change in that direction is the magnitude of the gradient. Here's the way I like to say it. The gradient has a geometric interpretation. Gradient's a vector. Vectors are defined by a direction and a magnitude. And so forget about the previous formula momentarily. Forget about the previous formula we have for gradient. Let's just observe that I can understand the gradient vector simply by telling you about its direction and its magnitude. The direction is the direction of fastest increase. It points in the direction the function's increasing the fastest. And the magnitude is the rate of change in that direction. Okay. All right, so it's kind of a geometric characterization of the gradient. And that's really interesting because, the gradient vector is computable by partial derivatives. That's where we first wrote it down in the first place. We were writing down Jacobian matrices with partial derivatives. And then we said, hey, let's, in a certain special case, this is a vector. Let's call it the gradient. It's made up of partial derivatives, easy to compute. Geometrically, excuse me. Gosh, God, I'm sorry. Geometrically, its geometric characteristics are natural, meaningful things. All right, I do want to make a quick observation about how to phrase these results. I like to call the direction of fastest increase. That's a very general term. We got a function, we're trying to make it increase. This is the direction you go to make it increase as fast as possible. I think it's very natural terminology. It's also sometimes called the direction of steepest ascent. Now here's my problem with that. Steepest ascent, how am I ascending? How is f ascending if I'm looking at f from this point of view? Answer, it's not. Right? The idea of calling it ascent is if you're not looking at the function this way, but if you're specifically and narrowly and only looking at the function as a graph. If you're looking at the function as a graph, then okay, yeah, sure. Well, let's draw a graph of a function like this. We have a kind of a domain down here, if you will, and then the target we represent with the vertical. That's what a graph is. A graph is z equals the value of the function, right, at input point x and y. And if you were to draw the graph, then yeah, okay, so the graph would be some surface. And you could talk about, well, given some point in the domain, and, looking up on the graph and asking, which way should I go in the domain to make the function increase the fastest, and the values of the function, we're going to be looking at slopes, how steep are these slopes as we move along that graph in those, directions that we're considering. And then, the one that makes the function increase the fastest is, in fact, no surprise, I hit the wrong, is the one, the one that makes the function increase the fastest is the one where that's sort of directly uphill, if you will, on the graph. And so you could call it, that's the direction in which the graph is the steepest. So direction of steepest ascent makes sense in this context if you're looking at it as by way of its graph. And so that's my problem with this terminology. I might not want to be looking at it from the point of view of its graph. Don't make me interpret functions in terms of graphs. Very often I can't look at the graph. What if I have 3 input variables and 1 output variable? I can't draw the graph. It's 4-dimensional. That's a problem. Right? So independent, though, of how you're looking at it, it is always the case that we're looking at the direction in which the function's increasing the fastest. Yeah?
How do you derive the direction of the gradient? Or is it just a definition?
You what now?
So is the direction of gradient a definition?
So remember, a vector is made up of 2 things. It's made up of a direction and a magnitude. And this is just kind of the geometric point of view. This is how we just think about vectors. But if I give you a vector and maybe I give you its coordinates, and let's suppose the vector is that vector there, it's pointing in that direction. So yeah.
The direction of that vector, is it defined in a way that it is the fastest increase, or is there?
No, we just proved a theorem. No, we didn't define it to be the answer to the question. We asked the question, and we did a little study, right? Here's our question. What's the, what direction maximizes the directional derivative? And we compute, argue, and came up with this as our answer. That's not a definition. That's a result. Yeah. Right. Okay. All right. So, likewise, slope, thinking about the magnitude of the gradient as being the slope. Well, it's the slope of the graph. Yeah, that's true. If you happen to be looking at a graph, then yes, that's right. But you might not be looking at a graph. It might not be possible to look at a graph. The magnitude is always, though, the rate of change with respect to distance as you're moving in the optimal direction in the domain. That's what it always is. May or may not be looking at a graph, and so it may or may not have anything to do with there being a slope of anything. Okay. All right, but nevertheless, honestly, I think this term here is probably more common than fastest increase. So heads up, you're going to see it. It's out there, and I encourage you to, when you see that, think direction of fastest increase. Okay, got to move on. Here's another interesting property of gradient vectors. Gradient vectors, very weirdly, gradients are always orthogonal to level sets of that function whose gradient you're looking at. And that's pretty weird, right? Y'all remember level sets. We didn't say anything about gradients at the time, right? Previously we were talking about gradients. We didn't say anything about level sets at the time. They're pretty separate conversations so far in this course. So, amazing fact, they're always orthogonal. And actually, it's not that hard to see why this is true. Let me show you an example. So here, by the way, I'm going to be looking in the domain. Everything that we're going to do in this analysis takes place just in the domain, so we're not looking at graphs, right? Again, it's a very narrow kind of point of view on a function. Looking at the domain, now what is a level set? A level set, you'll recall, is where we take the function, set it equal to some constant, and that gives you an equation which then gives you a surface in the domain. So, for example, there's a surface in the domain. Here we're letting n equal 3. Let me put that where n equals 3. So 3 variables in the domain. All right. So the assertion that I'm making is that the gradient vector is perpendicular to that surface. Now, before I assume that, let me show you why it's true. It's a pretty easy argument. Keep in mind, this being a level set, f is constant. So as I am moving along this level set, f is constant. That means the function's not changing. That means that my differentials are 0. Right? Now, as I'm moving along this level set, of course, I could represent my differentials, my position differentials, dx, by tangent vectors. Right? Bunch of different possible tangent vectors I could be thinking about that represent my position differentials. Right? What does this tell me about df? Well, I know that the whole idea here is that the function's not changing. F is a constant, so df is equal to 0. Here's the formula, however, for df. df is that dot product, gradient dot dx. So that means that this dot product is 0. Now, what could the gradient possibly be? Right? The gradient, by virtue of this picture, has to be a vector that's, there it is, perpendicular, well, orthogonal, right? Orthogonal. It's got to be a vector that's orthogonal to all of these tangent vectors. And if it's orthogonal to all of those tangent vectors to the level set, then it's got to be, unless it's 0, perpendicular to the level set. Yeah, like I say, pretty straightforward argument. So here's the punchline. Again, so the gradient is always perpendicular, orthogonal to the level sets. Yep.
Does that mean if you're given the gradient at like a point, you can find the equation for the level set's not a plane?
Well, the level set's not a plane, but you can talk. I was like all ready for you to get that. Yeah, no, we're hitting right on it. No, if you look at the tangent plane to the level set, you can totally find the equation of the tangent plane and we're going to do exactly that. Okay. Because the gradient, you can just treat that as your normal vector because it is, right? And if you're given a point specifically on the level set at which you want to find that tangent plane, you got a point, you got a normal vector, you got yourself a tangent plane. So, in fact, that's exactly how we're going to address this next question. Next question is, now, the next question is a question we've already considered previously. We already know the answer to this question. So, what I'm going to show you here is not really so much new result as new point of view on an old result. And that is to, what is the equation of the tangent plane of a graph? And remember, the idea is that if you give me a function and I'm looking at its graph, I can talk about the linear approximation of the function. Linear approximations we wrote down from an algebraic point of view. The graph of the linear approximation is the tangent plane to the graph of the original function. All right, so tangent plane to a graph, we know how to do that. Just linear approximation, take the graph of that. So let's take a different point of view. Let's think about the graph. What is a graph? Here's what a graph is. A graph is an equation that looks like that. And I want to use her observation. Her observation was, hey, if we were looking at a level set, then I could use the gradient vector as a normal vector in attempting to find the tangent plane to that level set. If only we were looking at a level set. And the thing is, here we aren't. Right, we're looking at a graph, not a level set. It's a bummer. Right? But now I'm going to call back. I don't know if y'all remember, we were talking about level sets and graphs and the relationships between them, and I made an observation that every graph is a level set of a different function, and it's this little move here, this little, subtract everything over to the other side, trickery, right? But so graph means set equal to z. Level set means set equal to 0, right? And then just notice that, well, by that argument, then the graph of f is the exact same equation as this 0 level set of that new function that I just made up, z minus f. It's a slick move, taking in, if you will, the right side of the equation and just whipping it over to the left side, and what had been a graph now becomes a level set. Great move. Of course, it's a level set of a different function. Got to be careful which function you pick, right? Okay. Neat little sleight of hand. But again, the question was we wanted to find the tangent plane to a graph. We were given the surface as a graph, and we have just chosen to say phooey on that. I want to view that as being a level set, and now it is. It's a level set of that function. And I like level sets because I know stuff about level sets, right? Level sets... level sets, I know a vector perpendicular to them. Gradient vector is perpendicular to it. So, no problem. I can just take the gradient of this function, take that function, take its gradient, and I can use that then as my normal vector. Everybody happy? Then it's all downhill from here. But again, if you're looking at a graph, if you've got some point, some values a and b, and if you plug that in, remember your original equation was z equals f of xy, and so if you plug in and see what the corresponding z value is, well, it's z equals f of ab. Right? Then your point that you're actually looking at, this point, is a comma b comma f of ab. There's your x naught. There's your normal vector to the graph, aka level set, now that we're thinking about it, different function. And n dot x equals n dot x naught. Right? Multiply it out. Right? Here's n dot x. N dot x naught is, excuse me, I'm sorry. I rewrote the x minus x naught over to here. So there's your n. Your x minus x naught is that. And multiply it out, collect terms, throw things around to make them look better. And there's your equation for your tangent plane. Old news, again, this tangent plane is, and you can see it right here, literally, it's the graph of the linear approximation. And we already knew that, right? So this is not new information, but this is a new point of view on this old result. And I think pretty nice. Okay, one of the big lessons here is in how we made this switcheroo from thinking about the graph of one function f to instead thinking about that same exact surface as being a level set of a different function g. Right, so make sure that you can do this. Make sure you can properly interpret what is the exact equation for the graph of f. How would I rewrite that as a level set of something, and what is that something? It's an important move. Essential to this argument we just made here. Okay. All right. Gosh, excuse me. Oh, man. Okay, so we're kind of done with Chapter 13 for a little while. Now, confession, I have skipped 3 sections of chapter 13. We've skipped 13.5, 13.9, and 13.10. We're skipping kind of right now. We are going to come back and do those later. I like to do those later because they're not part of the prerequisite trail for chapter 15. Chapter 15 is where this course gets really challenging. Right? So I think it's important, this is just my opinion as a teacher, I think it's important to get to chapter 15 as fast as we possibly can. Anything that's not part of the prerequisite trail for chapter 15, I would like to move to after chapter 15. And tragically, there's very little in the course that is not part of the prerequisite trail for chapter 15. So really, the optimization stuff in those 3 sections of chapter 13, that's really all I can afford. I mean, we just we can't procrastinate other things. So anyway, that's why we're skipping those. We will come back after we're done with chapter 15. So moving along now to chapter 14, I want to talk about integrals. The very first thing I want to make sure everyone is comfortable with is the idea that integrals are Riemann sums. Now I know that this is a little bit inconsistent with what you might have sort of taken away from a high school class. Some high school classes even skip Riemann sums altogether. That's a crime. It's a problem, right? And I want to show you why. But real quick, I mean, common misconceptions. A lot of people think that integrals, most fundamentally, deep down, I mean, cornerstone point of view on integrals is that integrals are area under a curve. And that's a mistake. That's a nice application, I suppose, but honestly, out there in the real world when you're actually doing things with calculus, it's actually pretty rare that you need to compute the area under something. Surprisingly rare. Right? So it's not a good cornerstone point of view. Another common point of view is that the definition of an integral is, well, it's capital F of B minus capital F of A. I mean, that's how you always compute integrals, so isn't that the definition? No, that's not a definition. That's a theorem, right? So F of B minus F of A is a nice formula that can allow you to compute integrals, but it remains then what is actually an integral, right? Another awkward misconception is that integrals are antiderivatives. They've even reinforced that bad point of view with language. My least favorite term in all of math, the phrase indefinite integral. It means antiderivative. Say antiderivative. Antiderivative is more explicitly telling you, okay, I mean, I want to undo the derivative that I just took, right? So antiderivative is extremely natural terminology. Why conflate and make it look like antiderivatives are actually identical to integrals? It just creates confusion. Again, this is one of my little soapbox, little pet peeve topics. Okay, so all of those are not definitions. Those are, things that are, I suppose, maybe or maybe not true in some sense, right? But they're not cornerstone definition fundamentally what integrals are. Okay, so what are integrals? Integrals are Riemann sums. That's what an integral is, as far as this class is concerned. Side note, there are other kinds of integrals. It's a whole long story. But as far as Math 212 is concerned, this is what an integral is. Okay. Why does this matter? I kind of always had the idea when I was in high school that Riemann sums were kind of that's the old-fashioned, outdated, low-tech way to compute integrals. The much better way to compute integrals is f of b minus f of a. And my gosh, after anyone's ever seen f of b minus f of a, why would anyone ever go back to Riemann sums ever again? Interesting historical note. F of b minus f of a is part of the fundamental theorem of calculus. 1666. Didn't start getting popularized until quite a bit later than that, which is also a pretty interesting story. But Riemann was not even born yet. So this is not the outdated, irrelevant point of view on integrals. This is 150 years later. Or more. I don't remember the exact dates. Okay, so here's why we care. Let me rephrase that. Here's why I think probably y'all care. Partly as a mathematician, I care about integrals because I like abstractions, and I don't need there to be applications for me to find something fascinating, right? But I sort of get that that's, not everybody's cup of tea, right? But I am pretty sure y'all care about applications, right? Econ uses calculus for its applications. Physics, chemistry, etc., engineering, oh my God, they all use integrals for applications. And when you have an application, whatever that application might be, the very first thing you do is you rewrite it as a Riemann sum. Example. Suppose you want to compute the amount of work that it takes to perform some task. Y'all remember work problems from Calc 2 classes? Okay. I want to compute the amount of work it takes to do some task. How is it, I beg, that it is somehow clear that work could just be reconceived of as area? It's not. Work is not area. These are really, really different things, right? And if your argument for, I could use integrals to compute work because, after all, work is area and area is integrals. And okay, but you said work is area. Where's this coming from? What's your justification for work is area? I don't get that. Right? That's a problem. What you can do is you can say work is a Riemann sum. You can say, look, I've got some task, this big task of I am here, but I want to be there. I want to know how much work does it take for me to move across this. I've got a big task. How much work does that take? I can break that up into smaller tasks, and I can add up the amount of work that it takes to do each one of these little smaller tasks. And then on each little small task, there's going to be, and it depends on the specifics of the problem, but there's going to be something that I'm going to multiply by, for example, how far did I move? Force times the distance, right? That little distance is a delta x. So what you can do very naturally is take this application of some work problem and you can rewrite it as a Riemann sum. Well, isn't it a good thing that we've defined integrals as Riemann sums? And then isn't it further a good thing that I have a theorem that allows me to compute integrals so that I can get a number answer? But notice, if you remove Riemann sum from this little diagram, you're dead in the water. You can't even start. You can't rewrite work as an integral unless integrals are Riemann sums. Okay, so anyway, look, I know I give a big sort of soapbox speech on this, but this is a really important idea. I want to make sure that everyone's good with this. If this is kind of news to you, I want to encourage you to watch I've got a video on this. It's like a half-hour video. It's on my miscellaneous topics playlist on my YouTube channel. It's called Integrals. And it talks about this and several other important misconceptions or awkwardnesses about how people think about integrals that need to be corrected before going on in a multivariable calculus class. So anyway, I encourage y'all to take a look at that. But anyway, I'll bet you most of y'all remember all this business. And what I want to go on and talk about now is how to generalize this to a multivariable setting. Oh, yeah, a question.
How do you pronounce the Greek letter underneath the sum of from n?
Greek letter E. This is the letter I.
That's just I.
That's just an I.
Oh,
yeah, as I goes from 1 to n. That's just my weird. Yeah, I write I's like that's kind of a cursive I. Yeah. Yeah. Yep. Right. Right. So how are we going to generalize this to a multivariable setting? I mean, here's our definition of an integral. That is intrinsically a single variable expression, right? Here it is. It's we're looking at the interval from A to B on the x-axis. That's single variable. So if I want to do something kind of like this, but in a multivariable context, I'm going to have to change it. And when you generalize something, you're going to take an existing idea and you're going to change certain aspects of it to apply it in a new context. But you're going to keep certain aspects too, because otherwise you're not really changing. You're not doing a different kind of the same thing. You're just doing something totally different, right? So I want to be able to use the word integral in other contexts, and so I have to figure out what is it about this that's intrinsic to an integral, and what is it about this that's just sort of a peculiarity of how I'm applying it in R1. Okay, and here's my take on that. We're taking some sort of a domain and chopping it up into pieces. Right now the domain is the interval from A to B. Chopping it into little pieces. Notice I did not say one-dimensional domain. It's one-dimensional in this specific instance, right? But I'm going to say, what I mean by integral is I'm going to take some domain. We'll reconsider our options later, and I'm going to chop it up into pieces. And then on each one of these little pieces, what I'm looking at is going to be the value of some function times the size of the piece. Now you can see that in the existing expression we have for Riemann sum. What's the function? It depends. What's your application? If you're computing work, maybe it's force. If you're computing mass, maybe it's density. If you're computing area, maybe it's height. Whatever, right? What that function is, what we're going to call the integrand, depends on the application. But in all cases, there's some function that's being multiplied by size. Okay. And then we're going to add them all up. And then we're going to take a limit to get rid of all those round-off errors. And so this is what I'm going to call sort of qualitatively, this is what I mean by integral, and the specifics up here are just how these ideas apply in a single variable setting. So I'm going to now take these ideas, and let's see if we can make sense out of these ideas in a two-dimensional setting, a two-dimensional domain, that is. This is going to be a double integral, as we're eventually going to call it. All right, so here's the idea. Oh, well, let me go back to the thing. We're going to take our domain and chop it up into pieces. Well, okay. No problem. Here's my domain. We're going to start with rectangles in R2. Here's a rectangle in R2. And can I chop that up into pieces? Sure. Go ahead. Right? I mean, it's just... There, see, chopped it up into pieces. No challenge there at all. Okay. Alrighty. Now, next thing, can I, on each one of those little pieces, can I multiply some function times the size of that piece? Well, look, we're going to have to work out some details here, but yeah, sure, no problem. On this little piece. Okay, now I'm going to have to get my hands dirty a little bit. Which piece, you might ask, right? The pieces that we referred to up here were indexed by, well, the numbers 1 through n. You chop up an interval, you number the pieces 1 through n. We've got a more complicated story here. Right? These pieces, I can't number them 1 through n. I've sliced it up in different ways in that direction, but I have also sliced up in different ways in that direction. I have n squared pieces. And they're not just in order. They're kind of zigzaggy or something. I mean, how am I going to index these? And the idea is each little piece that I get comes from a couple different kinds of slices. On the one hand, I got that by slicing up vertically. And in the process of slicing up vertically, notice I also sliced up this interval from A to B. And I'm going to index sort of horizontally, if you will, by I. Likewise, to get this piece, I also sliced up horizontally. In the process of slicing up horizontally, I also, as it happened, sliced up my interval from C to D. And I'm going to tell you where I am on the y-axis by indexing with this index J instead of I. Now, I and J are independent, right? I could be large and J could be small. They could both be large. I could be small and J could be large, right? There's all sorts. There's n squared different possibilities. I goes from 1 to n, J goes from 1 to n. But if you give me an I and a J, that tells you exactly which little piece I'm talking about. And so the idea then is, and some more details to be worked out, but where you are, you've got some point there. Plug it into some function. Whatever the function is, and by the way, again, what's the function? It depends on your application. Right? go back to here. I mean, this function, if you're talking about work, this is force. If you're talking about area, it's height. If you're talking about mass, it's density. The function depends on the application. Likewise here, what that function is, I don't know. It depends on the application. We'll get to that. But notice the size of the piece is now something I can also write down. Size, how big is that little piece? Well, easy formula. It's delta x times delta y. I mean, this is just, how wide. That's just b minus a over n. Delta x here, I'll say. B minus a over n. And this delta y over here, I'll use red, I guess. That little thickness there, delta y, well, that's just d minus c over n. So, I've multiplied some function as is defined in that box. Excuse me. Times the size of that piece. I'm just following the rules here, right? Value of some function times the size of the piece. And it's all over but the shouting at this point. Now I just have to add up over all the pieces and say limit, so I get to avoid all the little round off errors. And here is our expression. This is a, kind of a multivariable version, it seems. Still not sure what this looks like or, how useful is this for anything. But this is a multivariable version of the single variable integrals that we wrote on the previous page. Now, how's everybody doing so far? Does everybody see how this? I'm just following kind of the strategy from single variable integrals on the previous page. Is everybody on board with that? Okay. Cool. Quick observation, reminder, this is summation. This is not a summation as I goes from 1 to n, right? So I goes from 1 to n, sure. But that doesn't give you the whole rectangle, right? That you have to let I go from 1 to n for each value of j between 1 and n as well, right? So both I and j, both I and j have to go from 1 to n independently. You can't, if they're both always equal to each other, you just get the diagonal pieces. That's not what we're talking about. So we have independent indices, I and j, both going from 1 to n. Okay. All right, so this is called a double integral. And what's going to turn out to be the case, we're going to see some applications on the next page, but defining this thing called a double integral, we're going to use that notation for double integral, defining it as a Riemann sum. This is going to be analogously awesome for applications as doing the same thing for single variable, right? So remember, in the single variable context, who cares about Riemann sums? Oh, well, all of these applications, I can write them as Riemann sums. That's the point. And then calling that an integral and having tools for how to compute. Yeah, that's the finish of the problem. But the first step is connecting applications to Riemann sums. And likewise, we're going to see some examples on the next page coming up momentarily of, where applications can be rewritten as Riemann sums. Now, everybody good? Now, what about all this business, right? I mean, how are we going to actually compute this stuff out? I mean, we're not actually going to... Please tell me we're not actually going to compute, though, with Riemann sums, right? Everybody gets this chill down their spine of fear of having to... Am I going to compute with Riemann sums? What a nightmare. And I agree, yeah, for sure. That's not a good way to compute stuff. So there is an answer to this question. Yes, there's going to be a way to compute double integrals. I don't want to talk about that yet. We'll get to that at the right time, right? What I want to emphasize right now is how integrals are Riemann sums, and how the fact that integrals are Riemann sums are what allow me to connect to applications. That's what I want to focus on for the moment. Computing is all going to work out real nice. Trust me. Okay, so some applications. Suppose you want to compute the volume under the graph of some function. Now, reminder, a graph, there's the equation for a graph, z equals, some function of x and y. That's what a graph is, z equals. right? And given that graph, you could reasonably ask how much volume is sitting under that graph, right? I mean, it's kind of analogous to the question of area under a curve, specifically area under a curve that is a graph. Here we're just looking at the volume instead of area under a surface instead of a curve. That's a graph of a function of now two variables instead of one variable. That's otherwise highly analogous. Okay. Yeah, you can totally do this. Here's the idea. If you wanted to compute this volume, I first argue that grand total amount of volume there, all of that volume, that's the volume that you would get if you were to take this domain, chop it up into little pieces. On each piece, look at the amount of volume sitting over that one piece. Look at that amount of volume sitting over just that one piece, and then add up over all of the different pieces. Right? So now what is that amount of volume that we have there sitting over that one little piece of area? Well, okay, I mean, how much area do I have here? That little piece of area. I'm just going to call that dA. That's the area. And I argue that the volume is just, height times area. Height, of course, we're looking at height above the xy plane. Height is that z-coordinate. The z-coordinate is the value of the function because we're looking at a graph, right? That's what graphs are. And so that height is f of xy. So, I mean, the total problem that we were looking at, how am I going to compute the volume under this wacky surface thing that's the graph of some function? Well, this double integral strategy, this, what I like to call the chop it up, add it up strategy, will do that. Now, it remains, I don't know how to compute these things. We'll get to that in a minute, right? But if you were to take this great big thing and chop it up into a bunch of little French fries, right? You look at the volume of each French fry, add up the volumes of all the little French fries. That's the total volume. Everybody on board? Okay. All right. So this application, we can get our hands on it algebraically by thinking of it as a Riemann sum. Now, here's a totally different. Don't stop with this. Out in the real world, how often is it that you need to compute volumes under surfaces? Well, it's more often than you need to compute areas. I'll confess that, right? But it's not really the point. There's plenty of other things you might want to compute. Suppose I want to, for example, I have a sheet of metal here. Y'all remember applications in Calc 1 or Calc 2, which were to compute the mass of a one-dimensional metal rod. Y'all remember those problems? This is just a two-dimensional version of that. Suppose I have a two-dimensional sheet with a non-constant density. How would I compute the total mass inside of that sheet? Well, I chop it up into little pieces. On each little piece, I would take the area of that piece and multiply by, whatever the density is in, at that location. Now notice that's specifically the density at that location. Right? And density times area, mass per unit area times area gives you mass. Right? So the total amount of mass, I'm sorry, I hit the wrong color there. Total amount of mass, density times dA, added up over the entire domain, and you get another Riemann sum, aka double integral. Totally different physical problem, right? We're not computing a volume. This isn't a volume. If you start off as, you want to compute the mass of something? Okay, see, mass is really volume. Right? That doesn't make any sense. Mass isn't volume. Mass is a Riemann sum. We compute it with integrals because it's a Riemann sum. Okay. Suppose you want to compute the population of Wyoming or Colorado. By the way, side note, we are stuck with rectangles at this point, right? So we're only looking at rectangles in R2. So right now, the only states we can compute population of are Wyoming and Colorado. That's it, right? We'll talk about non-rectangular domains coming up soon. But if you want to compute a population and you've got population is distributed across the state in a non-constant way, right? Well, there's a lot of population density over here, and hardly anybody is over there, for example. Right? Well, yeah, okay, but on each little piece, if you're interested in how many people live in that piece, on that little tiny piece, if I were to take the area and multiply by number of people per unit area in that location, so at that spot, in that general vicinity, population density, people per unit area is going to be, hopefully somewhat constant around there. You can just say people per unit area times area. It gives you people. And then, again, as per usual, just add it up over all the pieces. There's your Riemann sum, aka double integral. Notice I did not say population is volume. That doesn't make any sense at all, right? But population is a Riemann sum. Okay. All right, let's see how we doing. We are out of time. So y'all have a great weekend. We'll pick up here on Monday. See ya.